Hello and welcome to part 3 of the fluid flow and heat transfer in a mixing elbow tutorial series. In this video, we will set up the simulation in ANSYS Fluent using the mesh generated in part 2. We will define material properties, apply boundary conditions, choose the turbulence model, and configure solver settings to capture both the fluid flow and heat transfer inside the mixing elbow. Finally, we will run the simulation and monitor convergence. So let's get started here. So this is the geometry and the mesh that we imported from Fluent Meshing. So here I can just modify some parts here. I will first use this ruler to see the dimensions. It is in meter. I will change it to inch as we change it in the Fluent Meshing also. For removing these arrows here for inlets and outlet, so I will go here and then click in this icon here to remove this one. I also go to mesh and display and use the edges to see the mesh inside the domain here. And as you see, this is a symmetry geometry. You can see all the parts and the boundary layers also here. We'll go to isometric view and one more time I will check the mesh. So in under the domain mesh, I will go on the check and perform a mesh check one more time here. I can increase the size of this window. So the check mesh will list the minimum and maximum X, Y, and Z values from the mesh in the default SI unit of meters. It will also report a number of other mesh features that are checked. Any errors in the mesh will be reported at this time. So ensure that the minimum volume here, this minimum volume is not negative, since ANSYS Fluent cannot begin the calculation when this is the case actually. Just notice this minimum and maximum values may vary slightly when running on different platforms, so no worries at all. Now I will go and set the working units for the first. I will decrease the size of the console, and as you can see, this unit is in the meter. So I will go to the domain and under the scale, I will change this view length unit from millimeter to inch. So you will see it will change automatically to inch. Then I can close this window. So now the working unit for length has now been set to inches here. But because the default SI units will be used for everything except length, there is no need to change any other units in this problem. And if you want a different working unit for lengths other than inches, so you can go under domain, mesh, and unit, and here you can just simply click here, press L on the keyboard, and then you can change the unit of length from inch to another part here also. But I will close this window and keep the inch for the geometry. In the next step, you will select the solver and specify physical models, material properties, and zoom conditions for your simulation using physics ribbon tab here. So now we are working on the physics tab here in this ribbon. I will retain this default setting here in the general, pressure based, and also the STD. And as this problem is a fluid flow and heat transfer, we need to enable the energy equation. So under the physics and models, I will activate the energy equation by just clicking on this energy equation here. Next part is defining our turbulence model. So again, under physics model and viscous this time, I can select on the viscous tab, and then here in the viscous model window, I will retain the K omega and uh, SST here for the viscous model, and just be sure that this production limiter has been selected in this case. Just in short, for this production limiter, actually this production limiter in the K omega SST model prevents realistically high turbulence generation by capping the production term in the K equation, in this K omega turbulence model. This improves physical realism and helps numerical stability, especially in complex flows with a strong velocity gradient. So I will keep this production limiter in this model. So now I will keep the default values here and just press on the OK. So we don't need other models here. So I will go to the next task, the material. So I will click on the create or edit material here. I'm just going to use the water liquid. So I will go to Fluent database here, click on it. And then if you move down at the end of the list, you can select the water liquid here, and just be ensured that only this water liquid has been selected. So click here and then copy into your material and then close this window. And now you have this water liquid in your material. So you can just close this window. If I go to material and under the fluid, you will see this water liquid has been added to your fluid into under the material here. Okay, so after this part, I will go to the zone and select this cell zone. So now here, I can edit this cell zone by double clicking on this part. I will just change this name to Floyd, and then change the material name and the material type from air, which is a default material, to water liquid, and then press on the apply, and then close this. And now it's time to go to set our boundary conditions. I will click here on the boundaries under the zones here. So we can arrange this boundary conditions based on the different types of this boundary condition. So you can go here, and under this group by, you can select the zone type. So they will be arranged based on the type of these boundary conditions. We have inlet, internal, outlet, symmetry, and wall for this boundary condition. Okay, first of all, I'm going to edit this cold inlet, so I can double click on this cold inlet, or just press on the edit and edit this boundary condition. Okay, so here we can go to our description. So as this is the cold inlet, the velocity is 0.4 meter per second, and the temperature is 20 Celsius here, and the intensity we will consider for both inlet as 5%. So I will just write here the velocity magnitude as 0.4 meter per second, and then change the turbulence from intensity and viscosity ratio to intensity and hydraulic diameter. So I will keep this one as 5 and change this hydraulic diameter to just 4, which is roughly the diameter of the inlet. Okay, so I will keep this one as here, and then I will go to the thermal tab and then change this temperature to 293.15 Kelvin, which is equal to 20 Celsius. So I will change this one and then apply and close this window. Next, I can go to hot inlet, press on edit this time to open this window. So this is velocity inlet and this is for hot inlet. So we can go again and check. The velocity is 1.2. So I will change this value to 1.2 meter per second. This time again, I will change to intensity and hydraulic diameter. Keep 5% for intensity. And for hydraulic diameter, I will change this one to 1 as this diameter of this pipe is roughly 1 inch. And for the temperature, as the thermal temperature and the temperature of this inlet was for this Celsius, so I will change this one to 313.15 Kelvin. And now I can apply these changes and then close this window. Now I will go and edit the outlet boundary condition. We can go and check. So I will keep all this default setting. Just I will change this backflow turbulent viscosity ratio to 4. And in the thermal tab here, you don't need to set a backflow temperature in this case, in this thermal tab, because the material properties are not functions of temperature. If they were, a flow weighted average of the inlet condition would be a good starting value. So now I can click on apply and then close this one. And for the wall boundary condition, I will edit open the window for a wall elbow first. I will retain all this default setting and also this heat flux to 0. It means that this wall is a adiabatic wall. So this is a adiabatic wall. It means that it's perfectly insulated and no heat in or out from this surface. So I will click on apply here and then close this one. I will just open this wall inlet also to check this window. So I will keep all this default setting and also keep this heat flux as 0 for this wall inlet and then apply again and close this window. So in the following step, you will set up and run the calculation using a solution ribbon tab. So I will go to the solution. First, I will go to the methods and I will keep all this default and I will keep all of this default setting for method. Then I will go to the reports and under this report, residual, and I will keep all of this value as the default and just be sure that this plot and print to console has been checked here. So now I can OK and close this. So now I'm going to create a surface report definition of average temperature at the outlet here at the outlet. So I will go under the report and definition and then here under this new surface report, I will select this surface report and then we will search for mass weighted average. So I will select this mass weighted average here. Okay, so for the name, I will call it as outlet temperature average. And then here, I will select all this report file, report plot, and print to console here. So during a solution run, ANSYS Fluent will write solution convergence data in a report file, plot the solution convergence history in a graphic window, and finally print the values of the report definition here into the console. I will change this frequency to 3. So this setting instructs the ANSYS Fluent to update the plot of the surface report, write data to a file, and print data in the console after every 3 iterations during the solution. You will see after run the calculation. And here in the field variable, I will select the temperature and check this one. It should be static temperature. And here under the surface, I will select this outlet, this surface, to has this mass weighted average report on this surface here. So now I can click on OK to close this. So I will go to the outline view, and then here, as you can see under this monitor, you have this report file that we have recently created, and also the plot. You can just simply edit and be ensured that this outlet temperature average is selected under this selected report definition. So as you can see, the Fluent automatically create this following items here. File and the so and you'll see it will get data every 3 iterations. So I can just close this window. Okay. Then now I'm going to add one more convergence conditions actually here. So under this report, I can select this convergence here. So as you can see, this convergence condition can add another conditions for the convergence process. Okay, I will extend this window a little bit. Then I will click on the add to add one more condition. I will call this one as a condition for outlet temperature average, this name. And then under this report definition, I can select this outlet temperature average that we have created. And I will change this stop criterion to 1e minus 5. And then I will write 20 for ignore iteration before, and enter 15 for use iterations. And I will click on the print to check this part and set this item to 3. So this new setting actually will cause Fluent to consider the solution converge when the surface report definition values for each of the previous 15 iteration here is within actually within this value 0.001% of the current value. So convergence of the values will be checked every 3 iterations here, and the first 20 iterations will be ignored, allowing for any initial solution dynamics to settle out. So note that the value printed to the console is the deviation between the current and previous iteration values only. So I will click on OK. So I will close this one. Next step and next task is to initialization. So I will keep this default and use the hybrid method for initialization. And then click on initialize. So this initialization process also has been done. So now I can go to the file and save the file, write, and the case. I will click here. I will just remove this one. So it is a 3D elbow case file, and then I will click on OK to save the file here. And before run, I need to uh, set up this run calculation. I will keep all these items as the default, and just number of iteration I will change to 150, and it is ready to run, so I can click on the calculate part. So you will see the process, and the simulation is running. You can go to different window here, and you can also set this as sub domain. You can see all these windows beside each other. If you want to go back to tab view again, you can just simply click on the tab view. Now this calculation has been done. I can click on the OK. This solution has been converged after 90 iterations. So actually the solution will be stopped by ANSYS Fluent when any of the following process has been done. One is the surface report definition, which we create here, converged to within the tolerance specified in the convergence condition dialog box, or the residual monitors converge to within the tolerance specified in the residual monitor dialog box, or the number of iteration, which is 150 in this case, in the run calculation task page has been reached. So if I extend this console, you will see the value of the iterations here. You can see these condition for outlet temperature, and then the value of the outlet temperature, also the residual for continuity, XYZ velocity or energy K omega equations here. So you can check this value here in the console. And then we can examine the mass flux reports for convergence using the results, and under the reports, so you can go to the fluxes here and select mass flow rate, and then two inlets and also the outlet. You can select all these three inlets and outlet boundary condition, and then press on the compute. You will see the net results is a very small value. So the sum of the flux for the inlets, these two hot and cold inlets, actually should be very close to the sum of the flux of the outlets here. So the net results here, as you can see, show that the imbalance in this case is well below the 0.2% criterion suggestion, so which is a very good value. So now I can close this flux report also. So you can always check this value for the case that you have inlets and outlets. So this net result should be a very small value. And actually the net imbalance should be less than 0.2% of the net flux through the domain. So now I can close this window and go to the file, write the data, and here I will just press on OK to save the data file. Okay, so that wraps up the simulation setup and the run for our mixing elbow case. We now have complete flow and temperature data ready for a visualization. In part 4, we will move on to post-processing in Fluent to analyze and present the results. Thanks for watching and see you in the final part.